Hello there. So today we are going to be finishing up this chapter. It had a lot in it. It was arithmetic sequences and series, geometric sequences and series. We did counting principle, combinations, permutations last lesson. Today we are talking about something that you guys have some familiarity with, and that is probability. If I said you flip a coin, what's the probability that you get heads? I would think that you would all know the answer to that. So, like I said, you do have some familiarity with the lesson already. We are going to scratch the surface, as I've mentioned, on probability. There is so much that goes into this stuff that it's actually pretty crazy. I had a semester long course solely devoted to probability in college, and it was probably my hardest math class. It was one of my more interesting math classes because you can apply it to a lot of places, but it was tough. It was probably my toughest math class that I took. But like I said, we're just doing one lesson today, scratching the surface, probably talk about some stuff that you guys already know, and then maybe add on to that knowledge that you guys have already. So we're going to start off with just a little bit of vocab, and then we're pretty much just going to dive into some problems and some problem solving techniques for you. So first of all, anytime you're talking about probability, there's going to be something that you do, and we call that the experiment. So an experiment is any happening for which a result is uncertain. For instance, flipping a coin is an experiment. Rolling a dice is an experiment. Drawing a card out of a deck of cards is an experiment. So that's, the thing that you're actually going to do. The outcomes are the possible results, like the things that could happen. You flip a coin, the outcomes are you could get heads, you could get tails. So the possible results of performing the experiment. The next two are the big ones. This right here is sample space. This is where probability all begins. This is the set of all possible outcomes. Basically, if you do something, how many total ways can the experiment happen? Like, how many ways can it end up? For instance, if you, again, flip a coin, there are two things that could happen. You either get heads or you get tails. That is the sample space. And the sample space is the most important thing because that's what goes in the denominator of your fraction when talking about probability. How many possible things can occur? Well, on the top of our fraction for probability is the event. How many ways can the thing happen that you want to happen? For instance, if I say you flip a coin, what's the probability you get heads? Heads is the event. Heads is the thing that you want to occur. So on bottom, it's how many things can happen. And on top, it's, okay, well, you perform this experiment. How many ways can the thing you want to happen? So these last two things are pretty much what compose your fractions for probability. Okay. The next one says enter the formula for probability. There's some interesting notation when you get into probability, but for the just talking about the skin and bones of probability today, I'm just going to try to get you to understand the concepts more than the notation. So really what we do to figure out the probability of an event happening is kind of what I already said. The denominator is your sample space. Sample space meaning how many things can happen. And that's why last lesson we talked about counting principle, combinations, permutations. We talked about how many ways can things occur. That's why we did that, was to lead into sample space. Your numerator is going to be the number of ways an event happens. This is how we compose our fraction when we're talking about a probability question. So when I say the number of ways an event happens, like we're going to be talking about drawing cards out of a deck of cards. And I might say, what's the probability that you draw a 7 out of a deck of cards? Well, now you have to think, okay, how many different cards are there? That's your sample space. And how many 7s are there? And that would be the number of ways the event happens. That would be 4. There's 4 7s out of 52 cards. So it'd be 4 out of 52. Within what range does probability fall? So if it's impossible for something to happen, obviously there's a 0% chance it occurs. So 0 is the low end. There can't be a negative chance of something happening. 0 is the lowest that probability can be. And the highest is 1. I'm going to talk about how we can write the numbers here in just a second, but we say it falls from 0 to 1. There could be at most a 100% chance of something happening. If I say flip a coin, what's the probability you get a heads or a tails? Well, there's a 100% chance you're going to get a heads or a tails. Okay? Now, I'm going to skip these next two because I think you know what it means for there to be low probability and high probability. Like, not a good chance of it happening, high chance of it happening. The way you can write your answers to a probability question, there are 3 ways you can write it. And I don't care how you guys do it. You can write it as a fraction. You can write it as a fraction. That's fine. You can write it as a percent. Or you can write your answer as a decimal. So to take you back to the coin thing, if I flip a coin and I say, what's the probability that you get a heads? Well, you can write that answer 3 different ways. You could say there's a 1 in 2 chance that you get a heads. You could say there's a 50% chance that you get a heads. Or you can write it as 0.5. All are acceptable. I would take any of them. Okay, let's dive into some problems and some examples, and let's kind of see what you know. I might have you try a couple of these on your own just to see how good you are with this stuff already. So it says 2 coins are tossed. 2 coins are tossed, right? You're going to flip one coin, you're going to flip another coin. What is the probability that one coin lands heads up and one coin lands tails up? Right? You flip 2 coins. What's the probability that you flip one, you get a heads, you flip the next one, you get a tails? I want you to write your answer. This one's always a fun one to do in class because I make you guys, write your answer or guess what you think it is. I want you guys to write your answer or think about it. All right. A lot of times students will say 1 in 4. And that's wrong. The answer is 1 in 2. You have a 50% chance of this happening. And a lot of times in class I get some crazy expressions like, no, that's not right. You're doing this problem wrong. Well, we're going to do some math, obviously, to figure probability. But in its most basic form for probability, you can just list out all the things that could possibly happen. Right? Here's what I mean by that. Let's think about all the things that could possibly happen if you flip one coin and then another coin. You could get a heads and a tails. You could get a heads and a heads. You could get tails, and then you could get a tails and a head. Like, these are the 4 things that could happen when you flip these 2 coins. Well, so if I list these out, there are 4 things that could happen. That's your sample space right there. Then we look at, okay, how many ways did the thing happen that I wanted to happen? So I wanted to get 1 coin heads up and 1 coin tails up. Look at how many ways that happened. This one, that happened, and this one, that happened. Out of the 4 things that could have happened, 2 yielded the result that I wanted. That would be your numerator. So there's a 2 in 4 chance. There are 4 things that could have happened. 2 of them were good. So you could write that as 2 out of 4. I don't care if you reduce your fractions. You could write 1/2, 50%, 0.5. All those answers are acceptable. So again, sometimes it's nice to go back to basics if the numbers are small enough and actually just list out the things that could happen. Some students tend to overthink probability. This was me. I struggled in college with this course because I would overthink things. But then at the same time, it's easy to underthink them as well, which is a really weird statement, but probability is tough. It's tough to write questions for probability. It's tough to answer them. There's a lot of things to take into consideration. Like I said, we're not going to get into a ton of those things in this lesson. All right, next one. Look at the chart. What's the probability the total of the two dice is 8 if you roll each die one time? So think of that. You're going to roll a die. You're going to roll another die. What's the probability you get a total of 8? Well, to start these problems, we always look at sample space first. How many things could happen? How many different possible ways could you roll these two dice? You know, on the last one, I listed out all the possible things that could happen. I'm not going to do that on this one because you could get a 1 and then a 6, a 1 and then a 5, a 1 and then a 4, 1 and then a 3, 1 and a 2, 1 and a 1. I mean, you got 6 options just there. I'm not going to list them all out. But if we think about sample space, this is where last lesson comes into play. Let's think about all the possible outcomes. All right, I roll the first die. Think about how many things could happen. Well, I roll the first die. There are 6 things I could get. I can get a 1, 2, 3, 4, 5, or 6. This is the counting principle from last class. We're filling in those blanks and then multiplying the things together. On the second die, there are also 6 things that could occur. That means there are 36 possible ways of rolling these two die. That's your sample space. There are 36 ways this could happen. Well, now let's think about how many ways can I get 8? Okay, well, if I roll a 1 on the first die, there's no possible way to get an 8. If I roll a 2 on the first die, well, the only way I can get an 8 is if I get a 6. So here's one way I get 8. 3 and a 5 would be a second way that I get an 8. 4 and 4 would be another way. I could get a 5 and then a 3. I could get a 6 and then a 2. So out of those 36 possible outcomes, 5 of them give me an 8. So to get a total of 8, we have a 5 in 36 chance of getting an 8. All right. Oops. There it is. Next. A player chooses 6 different numbers, 1 through 44, so you're going to play the lottery. All right, you're going to pick numbers. It says if the player matches all 6 numbers in order, now that probably matters for a reason we'll talk about here in a second, the player wins the top prize if you match all 6 numbers in order. What that means is, let's say you pick 6 numbers. Let's say you pick 5, 9, 12, 2, 30, 40. Okay, let's say those are your lotto numbers. And the numbers come out, let's say the first one's a 9, and then a 5, and then a 2, and then a 12, and then a 40, and a 30. Since it said in order, you technically matched no numbers, even though you got all 6 numbers right. That's not how the real lottery works. You don't have to get them in order. But that's what this problem says. What is the probability of winning the top prize if the player buys 1 ticket? Hint, what's the sample space? So we always start with the sample space. We always need something in the denominator of the fraction. So we need to think, how many ways can these numbers come out of the machine? Since it says in order, that tells me it's a permutation problem. What that means is there are 44 numbers. How many different ways can 6 balls or 6 numbers come out since they have to come out in certain order? This is a permutation. That means that in the denominator, we have 44 permute 6. This is going to tell us how many different ways the balls can come out of this machine right here in different orders. I have that written down. I would do that in my calculator, but it's 5,082,517,440. So 5,082,517,440 possible ways the balls can come out of this machine. You buy 1 ticket. That means out of all these things that could happen, you have one good thing that could happen. You have a 1 in 5 billion chance of winning this lottery. Now, if you buy 2 tickets, think about this. If you buy 2 tickets, you just doubled your chances of winning the lottery. You doubled it because you would just be having a 2 on top instead of a 1. You would still have a 2 in 5 billion chance of winning, but you did double your chances, right? But there it is. It's pretty tough. All right, the last couple of things we're going to talk about. So I play a lot of poker with my friends, and I have to do a lot of thinking. I do a lot of math. I do a lot of probability to figure out if I want to call a certain bet, or what are the chances I'm going to get a certain card that I need. Is it worth putting in the money for those chances? Things like that. There's a ton of math that goes into if you're playing cards. Well, the last thing we're going to talk about, you can have questions where you need one thing or another thing to happen. Or you can have questions where you need something to occur, but then you need something else to occur. Right? Like an or question might be, I either need to get a 7 or I need to get a heart. If I get a 7, that's good. If I get a heart, that's also good. A 7 or a heart make me a winner. So an or case is giving you more possible ways to win, more good things that you would put in the numerator. And questions are tough. Like it's tough to win, meaning I have to get a 7, and then on the next card, I have to get a 2. That's tough. The first time you have to get a 7, but then you need something else to occur to win. So and questions lower your probability because you need multiple things to happen to technically win. Or things is easier to occur because you need something to happen or you need something else to happen. You have greater odds. So it says, how do you find probability of mutually exclusive events? I like to think about those as or questions, which I'll show you some examples here in a second. So basically, you take the probability. Let's say I needed to get a 7 or I needed to get a 2, right? I take the probability that I would get a 7. What are the chances of that happening? Plus, I have better odds because I also win if I get a 2. So I figure the big thing of this is to know you're adding. It's an or question, you're adding the probabilities together. The probability of one thing happening plus the probability of the second thing happening are your chances of one of those two things happening. One card is selected at random from an ordinary deck of 52 playing cards. So you do need to know a little bit about cards. I'm going to write some, I've learned over the years that I thought this was common knowledge, but, some students don't know this. In a deck of cards, you have 4 suits. You have diamonds, you have hearts, you have spades. I'm terrible at drawing a spade. And then you have club. Something like that. So there's 4 suits. Within each suit, you have a 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, ace. So in each suit, that's what you have. You have 13 cards. So you have 13 diamonds, 13 hearts, 13 spades, 13 clubs. That's 52 cards total. We're not going to have jokers taken in. It's just an ordinary deck of 52 cards. Okay. We're going to take one card. What's the probability the card is an even numbered card? Well, first we have to think about sample space. If you draw one card, how many different possible outcomes can you have? Well, there's 52 cards in the deck. That's your sample space. Then I need to think, okay, how many even numbered cards are there? Well, there's 1, 2, 3, 4, 5. Just in one suit alone, there's 4 suits, which means there's 20 even cards. So if you draw one card, you have a 20 out of 52 chance. And I'd be okay if you left that answer, but it reduces to 5/13. Now, the reason this is kind of under the or portion of the notes is because another way you could think about it is in each suit, there are 13 cards, and there's 5 even cards. So you have a 5 in 13 chance of pulling an even diamond, plus you have a 5 in 13 chance of getting an even number in the spades, plus you have a 5 in 13 chance of getting a heart. I forget which ones I've said already. And then 5 in 13 getting a club. So we could get an even numbered diamond, or we could get a club, or we can get a heart, or we can get a spade. You know, anytime we're using the word or, that's going to be your plus. You're adding. You're creating better odds, better probability. And if you add all those, that's not right. What in the poop did I just do? I don't know. Go with this one. I'll have to rethink on that. I'm probably going to think of that as I'm doing the rest of the notes now. B, the card is a heart or a diamond. A heart or a diamond. Okay, so again, sample space. We draw one card. We have 52 possible things that can occur. Well, let's think about our sample space. How many hearts are there? How many diamonds are there? There's 13 hearts, 13 diamonds, 26 out of 52, or 1 in 2 chance, which makes sense because if there's 4 suits, we're basically saying what are the chances we get 1 of 2 of those suits. So there's a 1 in 2 chance. The next one, the card is a 9 or a face card. A 9 or a face card. Okay, well, let's think about how many 9s there are. Let's do this a different way than we did in part B. Let's think about how many 9s there are. There are 4 9s. So we have a 4 in 52 chance of drawing a 9, right? You draw one card, you have a 4 out of 52 chance. If you get a 9, you win. Or if you get a face card, you also win. So plus, we have another chance to win. We could get a face card. So let's think about how many face cards there are. Face cards are jacks, queens, and kings. Those are cards that have faces on them. So there's 1, 2, 3 in each suit, which means there's 12 face cards total. So we have a 12 out of 52 chance of getting a face card. When we add these, we have a 16 out of 52 chance. We have a 16 out of 52 chance of getting a 9 or a face card. All right. And we could reduce that. That reduces to 4 out of 13. Next one. The card is either a heart or a face card. A heart or a face card. Now, this one is really interesting, and it's kind of fun to have students do. If you want to pause it and try it, this one, like I said, it's kind of fun. So mutually exclusive events, I kind of glossed over that term, but mutually exclusive events are when they have no outcomes in common, right? You have a 2, you're drawing a 2, you're drawing a 3. There aren't any 2s that are also 3s. However, for this one, there are face cards that are also hearts. And so we have to take that into consideration. Let me explain what I mean here. So if we're treating this like an OR case, well, let's first just think, what's the probability we get a heart? Okay, well, there's 13 hearts out of 52 cards. Okay. Or we also win if we get a face card. Well, we just said there's 12 face cards. Okay. So a lot of students would just put 25 out of 52. However, there are face cards that are also hearts, right? We accounted for 3 of these cards 2 times. The Jack, Queen, and King of hearts we accounted for here. We also accounted for here. So we need to remove those 3 cards that we counted twice. So we have to take away the 3 out of 52 cards that we accounted for twice. Now, another way of going about this is you can just list out all 52 cards and then try to find, the hearts and face cards. It's just a different way, but you get 11 out of 26. So anytime that there are things they have in common, you need to take that into consideration. All right. Then the last type is an and type, where you need something to happen and then you need something else to happen. It's harder to occur because you need more things to happen than just the first thing. So instead of getting into all the notation, well, in an or case, we're adding the probabilities. In an and case, we're multiplying the probabilities. So we take the probability of the first thing happening times the probability of the second thing happening. All right. What is the probability of picking one card from a standard deck of cards and having it be a king and a heart? You're trying to get a king and also a heart. This is kind of an interesting question because the easiest way to think about it is there's only one card that's a king and a heart. It's the king of hearts. So out of all 52 cards, there's only one card that's going to meet those conditions. But if we're talking about doing it the multiplication way, well, let's think about the probability of first just drawing a king. Okay? The probability of drawing a king. Well, there are 4 kings, right, out of 52 cards. That's the probability of drawing a king. And I need a heart. So there are 13 out of 52 hearts. Now you could actually multiply these fractions straight across. You can cross reduce or whatever you need. But if you would multiply these together, you end up getting 1 in 52. So it's just a different way of doing the same problem. All right, last one. A random number generator on a computer selects 3 integers from 1 to 20. What's the probability all 3 numbers are less than or equal to 5? So think about this. When I'm doing probability, I always think about how many ways can I win. When I say that, I'm not talking about gambling or anything like that. I'm just talking about how many ways can the thing that I want to happen. That's what I mean by win. So we have this random number generator and we push, give me a number, select. And it's going to spit out a number. And I need all 3 numbers to be less than or equal to 5. Well, let's just talk about the very first number. To win, I need the first one to be less than or equal to 5. It doesn't even matter what happens on the next 2 if the first one doesn't meet the condition. So we always have to start with the first thing. Well, let's think about the probability of getting a number less than or equal to 5. So to win, we need a 1, 2, 3, 4, or 5. So out of these 20 numbers, 5 of them are good. So there's a 5 in 20 chance of just the first number being a 5 or less. Then I need the second one to be 5 or less. So we have another chance. And the numbers can repeat. It doesn't say they can't repeat. And then the third one, there's a 5 in 20 chance. So this is the probability, the first one. And then I need this to happen. And then I need this to happen. So I'm going to multiply these together. And again, we can reduce or whatever. 5 and 20 is 1/4. 5 and 20 is 1/4. 1/4. So we would get a 1 in 64 chance of it happening. Which makes sense because if you only have a 1 in 4 chance of it happening the first time and you need it to happen 3 times, you don't have very good odds of that happening. That's what multiplication does. When you're multiplying fractions, it's making the denominator pretty big. And it's making your event tougher to happen. All right, let me know if you have any questions on the homework. Good luck.